Start. Is there anyone who wants? I have chocolate vanilla cupcakes. You want? Raise your hand if you want a chocolate cupcake. Raise your hand if you want a vanilla cupcake. Got my gloves in here. I'm all dirty. All right. Start with these. All right. So who wanted to do them, please? I'm so much stirred on this. I have to get them. Set of vanilla cupcakes. Got yes. Anyone else want a cupcake? Anyone want chocolate cupcake? All right, you guys have been doing so good, doing all your homeworks, doing all the quizzes, that I thought I would get you some cupcakes. You're welcome. Wasn't like there was a store sale or anything. Not like that. All right, so while you're eating your cupcakes, let's go through the announcements. Homework 4 is due next Thursday, so that's up in my classes now. And there's a quiz today, right? So topic, standard deviation, normal distributions. Remember those 3 numbers they have to memorize? Okay. Any questions on the announcements? All right. So what we're going to do, I am going to do this thing on, oh my goodness, on my iPad again. I kind of like the iPad. I feel like it's a little different than usual, but still like it. So, just gonna see. Oh, here we go. Oh, no. There's a way to make this full screen. I feel like if I click this a little bit. Nope, that didn't happen. There it is. Full screen. There we go. Okay, and I'm going to turn this around. All right. And if you didn't get a cupcake, or if you want one, I can give you one at the end of class. Okay, so I think we left off on Wednesday talking about the normal distribution and z-scores, right? Is there anyone who needs a set of guided notes? Maybe. Yeah, from yesterday. I think it was new yesterday. Yeah. All right. Anyone else? Okay. Here you go. All right. So, I mean, on the quiz, you're going to have to find the standard deviation. Oh. on the quiz, you're gonna have to find the standard deviation and do a little work about using the standard deviation to figure out like what percent of the population is between this number and that number, right? So we kind of talked about on Wednesday why standard deviations are so important. They're kind of like little markers that tell us like how much below the mean we are, how much above the mean we are. And it can be used for any distribution at all, right? We even talked about how, for example, if we didn't want to go just within one standard deviation or within 2 standard deviations or within 3 standard deviations of the mean and just memorize those 3 numbers, we actually can go like 1.5 standard deviations above the mean or -2 standard deviations above the mean, which is actually 2 standard deviations below the mean, right? And this was the concept of a z-score. So we talked about how z-scores are how much or how far away we are either above or below the mean, right? Okay. Then we kind of talked about how to find a z-score. So we had this nice formula here, z is equal to x minus the mean over the standard deviation, okay? So whenever we're given an x value, the mean, standard deviation, it's really easy to find the z-score. We even did some examples over here with our tests, right? So we're going to continue with this example. Teacher giving 3 different versions of a test. They all have different means, standard deviations. And we're going to talk about a little bit harder of a question. Rather than just finding someone's z-score, sometimes we're given the z-score and asked to find the data value, okay? So if we flip the page to the very back page of your notes, okay, we have that Anna's z-score on test version 1 was -0.5, and we're asked for her test score, okay? Little different of a question than the previous 2, okay? And I'll kind of show you how you can even tell that this is a different question. How about this? The z-score formula has x, it's got the mean, it's got standard deviation, and it also has z, right? Now, whenever I'm given a word problem, I always like to write all my information down, mainly because I make mistakes. So how about we do this? Let's go through this question, fill in everything that we know, and then we'll know what to plug into the formula. So the z-score was -1.5. That has to be z, right? So z is -1.5. And then it tells us that we are working on version 1, right? So if we go back to the back page, it says that version 1 has a mean of 66 and a standard deviation of 4. Okay, so those are the 2 values that I'm going to write here, 66 and 4. Okay, well, I guess that leaves us with not knowing what x is, right? So what I'm going to do is just rewrite our formula just because I kind of like having it underneath my test question. Z equals x minus the mean all over the standard deviation. And I guess what we can do is just plug in, right? So z is -1.5. X, we don't know. The mean is 66. And it's all over the standard deviation, which is 4. So we're about here. Okay. Well, here's where things get a little tricky, right? We want to get x by itself, but there's a lot of stuff going on here. Any ideas on what we should do first?
Multiply 9 to 4 by 4.
Awesome, right? 4 is kind of the thing that's making things hard, right? The 966 is kind of trapped up top because it's all over 4, right? So let's try to undo that division. Okay? Undo division, multiply. And since we have an equation, everything we do on one side, we have to do to the other side, right? So I'm just going to take both sides of the equation and multiply by 4. Okay. So you can do this in your calculator on the left, but on the left-hand side, I got 4 times -1.5 is -6. Okay. And on the right-hand side, well, this is really convenient, right? Because the 4's cancel, right? So 4 up top, 4 on the bottom, cancel out. and we're left with x minus 66. So now that fraction's gone, we made this a little bit easier to solve, right? What should be my last step in solving for x? Add the 66, yeah, because we're undoing subtraction. Addition is the opposite of subtraction. So I guess on the left, we have 60, and on the right, we have x. X is by itself, which means we're done, right? So Anna's test score is 60%, not too good, but it's a word problem, doesn't affect us too much. All right. Any questions on how we did number 3? And does everyone see how it's different than number 1 and 2? Okay. How about this? Try number 4. I'll walk around to see if you're on the right track. And have you write your answer down. Like the whole problem?
Sure,
Okay.
yeah.
All right, let's come back to the front. Emma wrote her answer up, looks really nice. Do you kind of want to take us through your steps here?
So first, I figured out what I needed to find. So I figured out who he was, me, and so I found out I need to find the x. So I plugged into the equation. So it's 2 equals x minus 66 divided by 2. I multiplied the denominator by the 2. Got 4 equals x minus 66. Add the 66 to the other side, nicely with x. And that's 70.
Awesome. Okay. Any questions on number 4? All right, nice job, Emma. Yeah, so it kind of depends on what you're given in the question, whether you're solving for x or solving for z, right? But if you write all your information down, like Emma did, you're never going to be confused which one you're solving for, right? All right, that kind of closes off section 30.6. So I think what we're going to do is we're going to move on to a new section. Okay, so we're actually going to go into chapter 30. Okay, so switching chapters. And how about this? So graduates. All right. Now, what I'm gonna do here is stop sharing for 2 seconds. We're going to find it. Okay. Next, I'm going to draw this graph on the board really quickly. Should have done this before class. Okay, so starting a new chapter on correlation. Okay. Okay, so before, oh my, that is so disoriented. I can't do that. Nope, no for me. Okay, how about this? We're just gonna pin. Okay, so before we even talk about like this graph that I put on the board, let's kind of talk about how what we're dealing with now is going to be a little bit different. Okay, so before we've been finding like mean, median, mode, doing a lot of number manipulation, but we've only been working with one variable, right? So we've only had like X or Y or Z or something like that, but we only have one variable. Okay, chapter 30 is going to focus on when we have not just one, but two variables. Okay, so I'll give you an example of what this kind of looks like when we go into questions. And yeah, I brought this. Okay, what I'm going to do is put you in a situation. Okay, so let's just say you're living in an apartment. Okay, and you're living in some other different area that might have a different temperature. Okay, now wherever you live, you might have an average temperature, right? And since you're living in an apartment, you're going to get a heating bill, right? So every month you're going to get a nice heating bill. So how many of these do I have? Okay, how about this? I'm going to give each of you your temperature, so the place that you're living and the temperature it is, and I'm going to give you your heating bill. I'm the mailman. Okay. Heating bill. So for example, they only live somewhere that's 20 degrees, and her heating bill is 160 bucks. And I'll live somewhere that's 60 degrees, and her heating bill is $100. There you go. Okay, TJ lives somewhere where it's 120 degrees and this is the most beautiful. Okay. So everyone kind of has their own temperature and their own heating bill. Okay. So what I want you to do is pretend that the x-axis of this graph represents the average temperature, okay? And the y-axis represents the heating bill. What I want you to do is to stick your post-it note wherever you think your temperature and heating bill should belong. Okay, so whenever you feel ready, come up to the board and stick this up. Yep. I'll do mine.
Put it like on top of someone's.
Yeah, you can do that. Awesome. All right, let's take a look at our graph here. So it looks like each of you had temperature, which was one variable, and the other variable was your heating bill. And it almost seems like your temperature kind of affects your heating bill, right? Let's just take a look at this. What do I want to say about this? Okay, so each of these Post-it notes represents a data value, right? Each individual has a number for one variable and another number for another variable, okay? And if you kind of take a look at this, it kind of looks like there's a downward trend, right? It seems like as the temperature increases, it looks like your heating bill decreases. And that makes sense, right? I mean, if it's really hot, you wouldn't put on the heat, right? So it makes a lot of sense that as the x-axis would increase, the y values decrease. And we'll talk a little bit more about what this is actually called, but keep this in mind as we go into values. Now, what am I gonna do here? Oh, so another thing about this graph. Now, usually on a graph, there's like not Post-it notes, right? One thing that we can do is instead of writing a Post-it note, for example, temperature equals 120 and heat equals 80, we can literally just draw a dot, right? So on this graph, all these Post-it notes can be represented by dots, right? And if you want to, you could fill in your guiding notes with the actual dots for these values. And each dot has a corresponding thing called an ordered pair, okay? So ordered, and it's kind of like a shorthand notation. Instead of writing temp equals 120 and heat equals 80, we can literally just write 120, 80. It's kind of like code for the x value is 120 and the y value is 80, for example. Any questions on like ordered pairs and how we like draw a dot on the scatter plot instead of a Post-it note? What we just created is actually called a scatter plot, okay? And it's called a scatter plot because all of these Post-it notes and dots are just scattered around on this graph, right? So that's kind of why we call it that. And it's a nice visual representation of the trends that happen between the x-axis or the x variable and the y-axis or the x variable. We can kind of visually see if it's going down or up or if nothing's happening. And we'll talk about more how we use this and how we represent this mathematically. Okay, let me get the notes up here. Okay, so Zoom, oops, share screen, start, should pop up soon. Oh, there we go. Okay, so let's go to our notes. If you want to later, you can kind of just fill this in. You don't have to though. Okay, but we can always plot our points on the graph, right? Oh, this is the wrong set of notes, isn't it? This is my other class. Sorry. Okay, here we go. We have a different type of graph. Okay, so you could have filled that in. Here. Okay, I know this is kind of overkill, but if we have an x value of 2 and a y value of 3, our ordered pair would definitely be 2, 3, right? Okay, you can fill in the rest if you want to, but I think we're good on what ordered pair is. Okay, so the sentence above just says that we created a scatter plot. Scatter plots display bivariate data. So let me kind of talk about what this word means. Okay, well, that usually means two, right? Like bicycle, I don't know, I'm biracial. So anytime you have two things going into one word, use the word bi, it means two, okay? So two and variate means variables, right? So data that can be represented with two variables, for example, heating and temperature. I said that backwards, temperature and heating. We call that bivariate data. Let's flip our page. Yeah, put my notes. There it is. So bivariate data contains two pieces of information. And kind of like this graph, we can kind of see that sometimes as one variable increases, the other variable does something else, okay? And we call that correlation, okay? Correlation is literally just the relationship between the two variables, okay? Let's talk about the first type of correlation, which we call positive, okay? So two variables have a positive correlation is if we increase the x value, the y value also tends to increase. Okay? So basically, one variable does the same thing as the other variable. Okay. Some examples of this. I'm going to write a little bit smaller. Height and weight. Okay. A really tall person is probably going to weigh more than a really short person, right? Usually, as the height goes up, the weight also goes up. Okay. How about this? Food eaten plus happiness, right? The more food you eat, the more happy you are, right? So those two are two positively correlated variables. Okay. Let's take a look at this one. Two variables have a negative correlation if you increase one variable, but then the other one decreases. Okay, so as x goes up, y goes down. Okay. So let's think of examples of this. How about, I can think of a good one. Maybe the amount of time you study and the number of mistakes you make. On a test, right? So the more you study for a test, usually the less number of mistakes you're going to make on the exam. Okay. Can anyone think of another example of two negatively correlated variables? How on the board? Yeah, as temperature increases, the heating bill decreases, right? So this is another example of something that's negatively correlated. So I'm even going to write that down. Temperature plus heating bill. Okay. So those are two examples of things that are negatively correlated. As you can see by the graph, if things are negatively correlated, the graph is going to go down, right? Okay. But two things might not even be correlated. For example, there might be no increase or decrease as you increase the x value. So y might not really do anything. Okay, we call that no correlation. Okay, so we can even have positive, no correlation, or negative correlation. Let's just take a look at some examples here. We saw an example of a graph being negatively correlated. This is an example of a graph that is positively correlated, right? The values seem to be going up as x increases, right? So this is positive. Okay. I bet you can tell that this one's negative, right? I'll just put a negative sign. And then over here, well, it kind of looks like it's going down, but you really can't tell, right? All the points kind of just seem to be floating around and doesn't seem to be going up or down too much. So this one actually has no correlation. Okay. So does anyone have any questions, like given a graph telling if it's positive, negative, no correlation? Yeah.
Is there a positive correlation if those variables decrease?
Yeah, so you can even, okay, so over here, I said like, as x increases, y decreases, or y increases, right? Well, another way of saying that is as x decreases, y decreases, right? So basically, they do the same thing, whatever they're doing. Yeah. Okay. Any other questions on correlation? Okay. Let's just take a slight break from correlation. Sometimes we might think that one variable is causing the other variable to change, which is why we even make these charts in the first place. We might be wondering, I wonder if temperature makes the heating bill go down, right? Okay. So we have different words to kind of describe the x-axis and the y-axis. So instead of saying the x variable, the y variable, sometimes we might say the independent variable and the dependent variable, okay? Now, the independent variable is usually the thing that we think is changing something. That's usually what we put on the x-axis, right? So the x-axis is always called the independent variable, okay? While the y-axis is called the dependent variable. So for example, we have hours worked per week versus GPA score. The independent variable would be the hours worked, right? And the dependent variable would be the GPA. Any questions on independent versus dependent? Okay, just kind of different terms I use to describe things. Okay. Let's move on to the next page. Now, we know that there's positive, negative correlation, but we haven't really talked about like, can something be more positively correlated than something else? Or can something be more negatively correlated than another one? And the answer actually is yes, okay? Which is why we have this number called the correlation coefficient, okay? So the correlation coefficient, we use the term R to represent it, okay? And this is just a number that can describe how positive or negative a graph can be, okay? One thing about this number is that it can't be like 2 or negative 5,000, okay? It can only be between -1 and 1. It can be a decimal, it can be a fraction, as long as it's not below -1 or above +1. Okay? So 3 rules about this. If R is positive, positive correlation. If R is negative, negative correlation. And if R is 0, there's no correlation. Okay, might make more sense when we look at some examples. Okay, so taking a look at scatter plot 1, we have the R is equal to -0.996. Well, let's take a look at that graph. It's definitely going down, and it's so like negatively correlated that it almost looks like a straight line going down. Like they're very tight, close to a little line going all the way down, right? Okay, let's take a look at scatter plot 2. Well, this one's still negative, but it's 0.646, which is a little bit closer to 0 than 0.996, right? And you can even tell by the graph, like the points aren't like very close to a straight line. They're still going down, but they're kind of weakly going down. Does everyone kind of see that? Okay. If we go to scatter plot 3, well, it's still negative, but it's 0.3, which is closer to 0, right? And now the points are a little bit more spread apart. Definitely not a line going down, but they're still kind of going down, right? And scatter plot 4, we have -0.002, which is almost 0, right? And it seems like there's no correlation, but maybe it's slightly tilted down, but not really, right? So as you can see, the R values can be between -1 and +1. If it's closer to 1 or -1, it's going to look like a straight line going down or up, right? The closer it is to 0, the more spread out it becomes. Okay. Any questions on correlation and the correlation coefficient? All right. Okay, so one thing I'm sure you'll ask me towards the test, but I'm never going to ask you to like tell me what R is based on a graph, because it's really hard to be like, oh, this one's obviously -0.6, right? I will kind of require you to know that this is negative, right? Because it's going down, but I won't require you to know like R is 0.5 and R is 0.4, or the difference between those. Okay. All right, let's take a look at this graph here. Okay, here we have a scatter plot, kind of like this one, but we have a line on top of it, right? This blue line. We kind of talked about this when we talked about bias. Does anyone remember the name of this line? Yeah, the line of best fit, right? It's the line that we can put on top of these values that kind of fit the data the best, right? For example, I can draw any line that I wanted. I can draw this one, okay? But it's not the line of best fit because it doesn't represent the data very well, right? Okay, so we call this line the line of best fit. It best represents the data, and it doesn't actually tell us any of the specific data values. So why is this even important, right? The line of best fit is important because sometimes we don't have a data value for a specific X value. Take an example, maybe 451. Someone got a math score of 451. Well, we don't have the data value for X equals 451, okay? Well, the line of best fit is good because, well, we can use it to like estimate the Y value for any X value, right? No matter if there was a data point there or not. Okay. So does anyone have any questions about the concept of a line of best fit? Okay. All right. So we usually use this for approximation purposes, trying to approximate the Y value for a specific X value. Let's move on. We're going to do a lot of talking about the line of best fit, but before that, let's talk about lines in general. Okay? We're going to have equations of lines that have numbers in them, but it's really important to know what each of the numbers actually mean in a line. Okay? So let's take a look at this one. We have y equals negative 3x plus 2. Okay? Well, we have two numbers in here. We have negative 3 and we have positive 2, right? Now, my whole goal here is to graph the line, but first let's kind of go through what each of these numbers mean. Okay, get to my notes here. So when we have a line that has just an x, no like x squareds, x cubes, x to the fourth, anything like that, we call this a linear line. Okay, it's going to be a straight line, and it has two numbers, the slope and the y-intercept. Okay. Now, before I even go into this, I'm going to define what each of these mean. Okay. The slope is the number that's attached to x. Okay, so I'm going to write this. This is the number attached to x, and we'll talk about what it actually means a little bit. Okay. So if it's the number attached to x, what's the slope of this line? Negative 3, good. Okay, a lot of people write negative 3x for the slope. That isn't the right answer. Okay, you don't attach the x to the slope. The slope is just the number. Okay, then I guess by process of elimination, the y-intercept is the other number, right? So 2 is the y-intercept, okay? And the y-intercept is the number by itself. There's no x attached to it. Okay. So, I think when we talk about what these numbers actually mean, it's always good to start with the y-intercept because I feel like it's a little bit easy to understand what this number means, and it's easier to graph when we start with this number, okay? So first I'm going to draw a little graph. We have negative numbers here, so I'm going to kind of allow my graph to have negative values by making a coordinate plane in the middle, okay? And I'm going to make each of the little tick marks be 1. Two, 4, 5. These are negative. 1, 2, 3, 4. Okay. Let's start with the y-intercept. It's called the y-intercept. I don't really watch football, but does anyone know what it means to like intercept a ball? Yeah, what does it mean? Yeah, so for example, if someone's throwing a ball to another person, a third person can intercept the ball by like catching it before it hits the other person, right? Okay, so the y-intercept is basically where the line hits the y-axis, right? Okay, so the y-intercept is a point on the line, and it's definitely on the y-axis, right? So this is the y-axis, okay? So if the y-intercept is 2, well, the line's gotta hit the y-axis at 2, which means the point is vertically on that 2. Any questions on y-intercept? Okay. Let's talk about slope now. Does anyone remember what slope actually means?
It's like the steepness of the line, so it's y over x.
Yeah. So let me write that down. So slope is like the steepness. And it kind of tells us if the line is going like up or if it's going down too, right? So for example, if the slope was positive, the line's going up. And if the slope is negative, well, the line's going down, right? Okay. And I like how you said y over x. Another way you can write that is rise over run, right? So whenever a slope is a whole number, I always like to write it as a fraction over 1, right? We can always rewrite a number as that number over 1. Okay. So talking about the definition of slope, well, it's a rise over run, right? So, okay, let's think about this. Rise is on top, run is on the bottom. If we're rising -3, that means we're going down, right? So why don't we do this? We're going to start with 2, and we are going to rise -3. So go down 1, 2, 3. Can't really see that, right? Okay, so I just went down 3 points, and the run is on the bottom. The run tells us 1, right? Do we go to the right or to the left? To the right, right? I already accounted for that negative with the top one, right? So we don't really need to go to the left. We always go to the right towards the positive numbers, right? So I'm going to run 1 there. Okay, so I rose down 3 because it's negative, and I ran 1 to the right. Okay, so my final destination is right there. Any questions on how I got to the next point? Okay. If you want to, you can draw your line now. I'll do it again so you guys can see. Okay, so rising 3 or rising -3 means go down 3. 1, 2, 3, and then you run 1, right? Okay, so my next point is going to be down here. Okay. Okay. What about if I wanted to go to the left, right? There's definitely points to the left of the y-axis. Okay. Well, let's see. -3 over 1 is also +3 over -1, right? So instead of rising down 3, I can rise up 3 and then run to the left, right? So I can go 1, 2, 3, and then go 1 over, and that would be my next point. Right? Okay. So I got a bunch of points. I can make my line now, right? So I think there's a way to do this neatly. I'm going to connect my dots and finish my line. And that's how you make a line knowing the slope and the y-intercept. Okay. Any questions on using the slope to graph an equation? Okay. Here's what we'll do. Tomorrow we'll do another example of this, and I guess it's quiz time, right? All right. Let me turn this off.